Hi, today is all about water treatment. So let's dive in to explore this fascinating journey. Welcome to the fascinating world of water treatment. Get ready to uncover the secrets of turning ordinary water into safe and refreshing drink. In our journey today, we'll start with the basics of water treatment concept, discover how we make water safe for drinking using a range of methods and techniques. Next, we'll explore coagulation and flocculation, key processes that remove impurities and make water clean. Then we'll look at sedimentation and aeration, where big particles settle in tanks. Learn about the simple requirements for this important step. Moving on, we'll reveal filtration technologies. It's not just about filtering water, it's about making sure every drop is clean and pure. After that, we'll delve into water disinfection, crucial for keeping harmful microbes at bay and ensuring our water is safe to drink. Finally, we'll explore desalination technologies, uncovering how we remove salts from water to make it drinkable. Join us on this exciting journey through the world of water treatment. Let's unlock the wonder is together. Water treatment is a process that enhances the quality of water, incorporating both conventional or traditional methods and advanced treatment methods. The aim is to enhance water quality for a brighter tomorrow. Various water treatment processes are employed to guarantee safe drinking water for all. Conventional treatment focus on traditional methods like coagulation, flocculation, sand filtration, and chlorination, while advanced water treatment involves cutting-edge methods such as membrane filtration, reverse osmosis, and UV disinfection. Let's delve into coagulation, where particles into water are destabilized to improve clarity. Aluminum sulfate stands powerful coagulant in water treatment, widely used worldwide. In regions like Africa, Moringa olivia seed extract is a natural alternative, often employed in low-income countries. Moving on to the flocculation. Flocculation is a process focused on making particles thicker, bonding them together, giving them time to gather. Coagulation acts quickly, while flocculation proceeds at a gentle pace, highlighting the difference in speed between the two processes. Both coagulation and flocculation can be energy efficient by utilizing gravity or incorporating bubbles to slow down the motion of the flow. But how do we design these basins? Let's start with coagulation. We primarily consider the detention time, usually around 15 to 20 seconds, and the G value, the power, ranging from 500 to 3000 per second. Also, proper impeller design is crucial for optimal efficiency. Imagine designing a coagulation basin. First, we need to calculate the G value using a special formula. Then estimate the basin volume using the traditional formula. The formula is volume equal time multiplied by the flow. Time, I mean detention time. So don't forget to adjust the pH in your design. Now onto flocculation. For flocculation, we require more time. Detention time is around 15 to 60 minutes and less energy required, typically 20 to 100 per second. To ensure smooth mixing, bubbles are essential to slow down water movement. The design concept remains the same, just we need to adjust the numbers according to the standards and use the same formulas as shown. But how do we determine the proper coagulant dosage? Normally, we conduct a lab test called jar test. The idea is by adding different dosage and observing which one works best, we can ensure the dose meets the requirement effectively. Let's delve into sedimentation, also known as clarification. Sedimentation involves removing particles from water through gravitational settling. They are horizontal and circular types, each with its own advantages and disadvantages. But how do we design it? For clarification, we must consider several factors, including detention time, normally between 3 to 72 hours. Surface overflow rate, ranging from 20 to 70 meters per hour, and score and settling velocity should be considered. Additionally, buffers, wear loading rate, and tank height are critical considerations. So when designing a clarifier, we first must estimate the surface area using surface overflow rate and flow parameters. Then we determine the volume of the tank based on the detention time. However, it's crucial to check for score and settling velocity to ensure optimal performance. But what's the difference between score and settling velocity? Settling velocity focusing mainly on ensuring particles settle down and should be lower than score velocity. Now let's enter the world of aeration, where we tackle taste and outdoors by infusing oxygen into water. Cascade aeration. This method involves creating a cascade effect where water flows over a series of steps or trays, allowing it to come into contact with the air and absorb oxygen. This enhances the aeration process, promoting the removal of undesirable taste and odors. Air diffusion. In air diffusion, oxygen is introduced into water through fine bubbles produced by diffusers or aerators. These bubbles rise to the surface, facilitating the exchange of gases between water and air. This efficient method ensures thorough oxygenation of the water, effectively eliminating taste and odors. So whether it's through the dynamic cascade effect or the gentle bubbling of air diffusion, aeration plays a crucial role in enhancing water quality by removing taste and odors. Let's explore filtration technologies. Dive into the power of nature's sands. Granular filtration relies on natural materials like sand to purify water. It comes into two main types: rapid sand filtration and slow sand filtration. But how do we make and design granular filters? For rapid sand filtration, the design criteria rely on three parameters: filter rate, normally between 12 to 30 meter cube per hour per meter square; filter depth between 0.6 to 0.9 meter; medium size 0.45 to 0.5 millimeters. Backwashing involves pumping water from bottom to top and cleaning the filters by destabilization frequency when the filter is too slow. Let's decoding the design concept, which includes under drain systems and backwashing. The formula is A equal Q over V, where V, I mean here filter rate, while in the equation where V equal A times D, V here I mean the volume of the filter. For slow sand filtration, the design criteria is the same. Filter rate just between 0.4 to 1.2, filter depth between 0.6 to 0.9, medium size is finer, 0.15 to 0.35 millimeters. Slow sand filtration require a longer detention time and doesn't need backwashing. Similar design formula is required, as same as rapid sand filtration, just number will be changed. So from this picture, imagine the slow sand filtration. It is clear, I guess. Let's discover contrast: rapid sand filtration versus slow sand filtration. Rapid filters are fast but need backwashing, while slow sand filters are slow and don't require backwashing. There is even more. Other types of filters await. Targeted filters like activated carbon and ion exchange filters offer specialized purification. Activated carbon filters use carbon magic or coconut shells to remove outdoor and organic pollutant, improving water taste and odors. Ion exchange filter employs specialized resin to exchange ions with other ions, ideal for ion removal and say goodbye to water hardness. Let's enter the age of advanced technology, membrane technology. I will start with microfiltration. Microfiltration is a type of filtration process used to remove particles and microorganisms from a fluid by passing it through a porous membrane. This membrane has a microscopic sized pores, so this filter can tackle everything except ions and viruses. Now let's unveiling ultrafilters. Ultrafiltration membranes have pore size smaller than microfiltration types. It's better than microfiltration and it can remove even the largest viruses. Now let's shift to introduce nanofiltration, a breakthrough in filtration. Nanofilters or nanofiltration membrane have pores smaller than used in ultrafiltration, but larger than those in reverse osmosis. so it's effective in taking on viruses with accuracy, though less effective against ions. Let's address the household filters. For urban setting, most households rely on advanced membrane technologies like ultrafiltration membrane filters and activated carbon filters. Regarding poor communities, they rely on traditional filters like arsenic and fluoride removal systems, or using simple scale rapid sand filtration called biosand filtration. All these methods offer essential solutions for clean water access. Let's uncover disinfection methods. In our quest of cleaner water, we utilize several disinfection methods: boiling, chlorination, UV irradiation, and ozonation. Additionally, there is chloramine, another powerful disinfectant. Chlorinations compounds such as sodium hypochlorite, chlorine gas, calcium hypochlorite, and KMNO4 plus chlorine solution play crucial roles in water treatment. Chlorination occurs in two phases: pre-chlorination and primary chlorination. Primary chlorination is particularly vital to ensure the eradication of bacteria from water. Chlorination effectiveness is measured by contact time, or called CT value, and residual chlorine or residual disinfection. Understanding chlorination breakpoints. At the breakpoint where an excess of free chlorine available for disinfection. Remember, chlorine dose equals chlorine residual plus chlorine demand. I mean by chlorine demand is the chlorine needed to kill microorganisms in water, and residual chlorine is the remaining chlorine that should be exist to ensure water is disinfected during water transporting, whether by pipes or in elevated tanks. This graph illustrates the chlorine breakpoint stage, showcasing the formation of chloramine, the effectiveness of chlorine, and reaching a point of residual chlorine in water. The chlorination breakpoint refers to the point in the chlorination process where the demand for chlorine has been satisfied and excess free chlorine is present in the water. At this point, the chlorine concentration is higher than what is needed to react with the substance present in the water, such as ammonia and organic matter. Initially, when chlorine is added to water containing ammonia or organic compounds, it reacts to form combined chlorine compounds known as chloramine. Chloramines are effective disinfectants, but are less reactive than free chlorine. As more chlorine is added beyond the point of chloramine formation, the concentration of free chlorine in the water increases. This excess free chlorine is available for disinfection purpose and ensure that sufficient residual chlorine remains in the water to continue disinfection throughout the distribution system. Ever wondered how we measure the effectiveness of killing organisms in waters? Let's delve into the concept of log removal. Log removal quantifies the reduction in microorganisms present in water after disinfection. For instance, 1 log removal means 90% of organisms killed. 2 log removals means 99% of organisms killed, and so forth. CT value measures the effectiveness of chlorination in killing microorganisms. It's a vital metric monitored by regulatory agencies. So, to meet safety standards, the actual CT value must align with the required or standard CT value. So, if chlorination isn't an option, remember the timeless method of disinfection is boiling water. Now let's turn our attention to desalination technologies, a fascinating realm where we extract fresh water from saline sources. Desalination comes into various forms. We have multi-effect distillation, or MED, multi-stage flash distillation, called MSF, and reverse osmosis, RO. But wait, there is even more. We also have forward osmosis, vapor compression, electrodialysis. Now, let's take a journey through the efficiency of various treatment processes. This graph showcases coagulation, where bringing particles together, flocculations, forming flocks, sedimentation, effective for large particles removal, filtration, removal wide range of particles, disinfection, eliminate microorganisms, desalination, removing salts from water. So, by understanding water treatment, we unlock the potential to provide fresh water in regions where it's scarce. That's the end for today, and see you next time.